And the recording is rolling. So welcome to a new week, a new topic. For the next few weeks, we're going to be studying forces and Newton's laws. Now, all of forces is just a push or a pull. And you guys are going to get your hands on some spring scales today that measures forces. And forces are measured in Newtons, which you guys are a bit familiar with because you guys have used these a little bit before. Well, Newtons, right? Newtons measure force, like those hungry monkeys pulling on the bananas sort of thing. Okay, so no, I'll give you guys some more formal notes later this week, but today the main focus is going to be a lab, but I'll get to that later. So tell you guys what your next assignment is, and I've cleaned this up from last couple of weeks. Now, I don't know if you guys were keeping an eye on Google Classroom over the weekend or not, but I did post a bunch of documents. I did show up at the school over the weekend to print a bunch of stuff out. I was going to get those to you guys today, but every single printer I ran into was broken. So if you want to see the documents, they're on Google Classroom. I'm working on printing those out for you guys. But your guys' next homework, which is going to be due a couple of weeks from now, so 9/24, that's like 2 Fridays from now. I picked a few problems from Chapter 4 and a few problems from Chapter 5, and these are all also listed out on both Google Classroom and also on Focus. And just like last section, the number of problems that I cover in class will easily cover those. So as long as you're following along, then it'll be no problem. Now, the new idea I have that I think is a much better idea than what I had going before was I created a bonus homework assignment for you guys. I've already created a grade column in Focus for this. Now, this is exactly what it says, a bonus. So if you do these problems in addition to these, then I will give you some extra points. But by default, everybody's grade is set to exempt. So if you never did set out, it's not going to hurt you. And yeah, I think that I think this is a much better idea than what I had going on last couple weeks. So there you go, guys. Traditional homework, just follow along, you'll be fine. And then I could only do like so many problems, then I'll run out of time. Got other activities for you guys. So if you do these in addition, I might do a couple of these in class to see how the time pans out. Turn those in, then I'll give you guys some more points. Okay. Up to you how much independent practice and points you want from that. Right, so you guys just turned in your kinematic quiz, your take-home kinematic quiz, so thank you for doing that. You guys probably noticed that there's some new posters hanging around this room. So I want to go over those real fast, not in a whole lot of detail, but just to point out that these are here, just so that you're a little bit familiar with them. And so one of these that you guys are seeing hanging from the ceiling says Newton's laws of motion. And I didn't notice this until after I hung them out, but I noticed that if you're sitting in the back of the room, that some of the print on these is kind of small. So I do encourage you guys to get a closer look at these when you guys walk around the room later, or take pictures of these with your phone. You guys have probably learned Newton's laws of motion, hopefully in maybe a middle school science class or something. So there's law of inertia. There's the second law of motion is you can actually couch it as a formula. Net force is equal to mass times acceleration of an object. And then there's Newton's third law of motion. You guys ever heard for every active force, there's a reactive force equal to magnitude opposite direction? Okay. So, of course, we'll talk more about those later this week. I'll give you guys more formal notes later this week on all of these. Right? You guys will see all of these in your notes later. Okay. Next one, a block on an incline. Hey, you guys have seen this before. A block on an incline. Like, there's a specific reason that you guys have seen this before, because I was setting you guys up. I was prepping you for what's about to come. So block on an incline, hey, its weight pulls straight down, like a gravity force from the planet Earth pulling it down. You could break that into components. And now I'm adding more to the story. I'm telling you guys there's more forces that are popping up here. What you guys are looking at is actually called a free body diagram. That's just a diagram where all the forces are labeled as vectors. You got force. You can split this one into components, something like that. So that's coming up. Let's see that. I got a guy standing on a planet, and this planet is pulling him down with some force that could be equal to his weight. I'm going to represent weight this way. So this guy's mass times what would be the gravity free fall. We'll get more into all these details, of course. But guys, is the Earth pulling you down? Of course it is. Are you pulling the Earth up? But which is pulling harder? Remember, for every force, there's an equal and opposite reactive force. You think you pulling the Earth and the Earth pulling you? Probably the same. Okay. At some point, I'm sure we'll get to some elevator type problems. Maybe there's an elevator accelerating up and down. Actually, that's one of the parts of your lab today that you guys will get to experiment around with a little bit. What if there's an elevator accelerating upward or an elevator accelerating downward? How would those free body diagrams look like? You guys see some different force vectors going on. Maybe if this guy's standing on, say, like a bathroom scale, something like that. What is that reading? I bet it's going to be different. As you guys ever ridden an elevator, feel a little bit queasy as it's getting going and coming to a stop? Ooh, there's something different going on inside this box room. We're going to do some Atwood. This is a real classic setup. I'll have you guys do a whole lab, maybe 2 labs on Atwood. So if you have a pulley, a string, you got some weights, got a whole box of lab weights here with some hooks on them, little captain hook lab weights, hook up to the strings. What if the 2 weights were the same? It would probably just be stagnant, right? But if you stack more and more weight on one side, like this box is looking bigger than this box, I bet it's going to probably accelerate more in that direction, something like that. I wonder what's going to govern how much it accelerates, right? See, what you guys have known so far in this class, you guys have learned the kinematic rule. So, like, okay, if something is accelerating, I have equations that can handle like how fast it's going, how far it's going. But now we're getting to questions like, well, what causes acceleration? Or what if these masses are different? Exactly what will the acceleration be as a result of that? You can modify an Atwood machine, right? Like you guys just saw the classic, usually I call this like a double elevator Atwood because it looks like 2 elevators. Right? But what if you did something like this? What if you just had like a single elevator type setup and then you slung a string over, did something like this? I hope to have some time in class to have you guys also do this version of the lab. And when I do, I usually have you guys slip a Hot Wheels car underneath this one so that it's very low friction system. So you don't have to worry about that. So this top block has a lot of inertia due to its mass, but maybe its weight vector wouldn't actually drive the system so much. Yeah, think about that one. Okay. You know what? These pulleys, see where it says pulley. I did throw some red pulleys back on those lab stations today, so if you have a few spare minutes at the end of class today, I do encourage you to break out the string and the pulleys and get your hands on this and try this out. You got that? Oh, that's it. That's all the new posters. All the new posters right there. Got some other stuff I want to show you guys, though. I've got a puzzle for you guys. Puzzle cup time. Now, this cup here goes back hundreds of years ago. This looks like a normal cup, right? I'd buy that somewhere. Looks like all hot glued together. Nothing sketchy about that. Wait a minute. Is there a hole in the bottom of this cup? Is that a hole in the bottom? Oh, why would there be a hole in the bottom of this cup? Would that actually... Hold on a minute. There's something weird going on here. Oh, never mind. It's just a computer glitch. Okay. So, what about the other side? Hey, there's just like a straw hole there. I wonder if this even holds water. Let's find out. So let me fill this halfway with water. All right. This is a little bit risky. Put a little bit more in there, but okay. Yeah, okay. So it holds water. Okay, so maybe it is a normal cup after all. Right? Normal cup, hold water. It's back hundreds of years ago. Let me go put more water in it. I'm going to fill it to the brim. Okay. When you fill it to the brim, oh boy, now the water's leaking out the bottom. For the video, let me turn the camera so you can see that. Right. Yep, it's a quite filled cup, and there's definitely some, all the water's leaking out the bottom. Drain. Now, while that's draining, yeah, this is something that they would do a couple thousand years ago. Give some guests this kind of cup filled up halfway, and if they had a particularly greedy guest who say, "I want more water." I guess I don't know why you'd be a villain for being thirsty, but guess that would happen. And so they fill up, and then, oh no, what are you going to do? It just keeps leaking out until you guys saw. I didn't do anything. I just let it drain. Okay? And look at that. There's almost nothing left. Yeah, there's a little trickle of water, but basically the whole cup drained, didn't it? The whole cup drained. Whoa, what's going on there? So let me recap what you guys just saw. But on paper, draw a cross section of this thing. So what you guys just saw was, say I had some kind of weird cup going on where can't tell exactly what's going on, but what you do know is there's some kind of straw hole here and some kind of straw hole here. Okay. I filled it up halfway with water, and all the water just stays in the cup. Perfectly fine, no problem. I fill it all the way to the brim, in different story. It drains out the bottom. But the last catch, the last piece that's weird about this is that the water level doesn't just go back down to the previous level where it was perfectly fine before. Right? Before you fill up halfway, it just stayed. No, the entire cup drains. So question for you guys, and this is the puzzle, is how are these two straws connected on the inside? I mean, obviously it's not a straight shot because then it wouldn't have held water in the first place. But what is that connection? I want to give you guys at least a day, maybe two, to think about that. I'll come back to this later this week and see how many guys actually figured that out. There might be a couple of guys that know already, but if you do, then I'm going to give your classmates a chance to think about that one. That's a good puzzle cup going on right there. All right, let's get to today's real topic. All right, so spring scales lab. You guys did have a bunch of spring scales back in the lab station. There's string, scissors. There's even pulleys, although it's not actually part of this, but you want to see them. Right. There's a box of lab weights. You guys got all this stuff. Let's take a look at these spring scales because they're color coded. So the green one has the smallest spring constant. What that means is you only need a little bit of force to pull it. Look at that little tiny force. And it only goes up to 5 newtons, right? One side says grams, the other side says newtons. Technically, the gram side only works at the surface of Earth, but I mean, I know we're at the surface of Earth, right? But really, read newtons, because that tells you some kind of force, right? You put a force and it pulls it apart. Pulling is a kind of force. Push or pull, that's all a force is, right? Okay. Next one, the brown one. The brown one can go up to 10 newtons. Remember, the green one goes up to 5. The brown one can hold up to 10. This is kind of a middle type scale, so this is pretty versatile. Can handle small weights, big weights. The next one up is this white one, goes up to 30 newtons. And this gold one has the largest spring constant. It goes up to 50 newtons. That means that it's super stiff. But all kinds of force. It's really hard to stretch this thing because it's so stiff. It can hold so much weight. So some of these are good for smaller weights. Some are good for bigger ones. And got different kinds of scales here. Right. Now, what do I want you to do with this? So about to get you guys this paper. Like I said, all the copiers were broken over the weekend. So we're going to I wanted to give you guys one per person, but I'm not going to be able to do that. I had to print these all at home. So these are going to be back in the lab station, so you guys can put several names on the paper. Okay, so whoever's in your team, if you have like a team of 4, then just write 4 names on this. Okay, we're just going to have to do it this way. And this is really like 10 mini labs, right? There's 5 mini labs on the front, 5 mini labs on the back. Today is really an exploratory kind of day. It's like a structured sandbox kind of deal. So like, what would happen if you say like put them in this Y shape and then like stretch it out closer to a T shape? Or what would happen if you made a vertical chain? Or what would happen if you like slung a string over and started accelerating back and forth, or like dragged it across the table? So just do these one by one. If you keep a pretty good pace, you should be able to finish this by the end of class. Again, make sure all your names are on it, and I will walk around and help you guys out. So any questions so far? All right, so back to the lab station, and like I said, I'll put you guys